Hello, and again, welcome back to the second part of our module 19. We're talking about the central role of tricarboxylic acid cycle in metabolism. I've said this already, but we're going to see a couple of those. This will be a brief lecture. Let's take it off from there. Catabolism of all the fuel molecules, we call them the fuel. Let me write it down. Fuel molecules. Fuel molecules are the proteins, the carbohydrates, and the fatty acid. All of them feed into the citric acid cycle at one point or the other. Now, so that one makes it very central. Now, it is also constitute the source of starting material for the synthesis or biosynthesis of other molecules. So, it links all catabolism, it also links all anabolism. That is exactly what the TCA does. It connects to catabolism, all products will link there. It also links all anabolism or biosynthesis. Now, again, like I said, it's a complete cycle that doesn't want to be broken. If a component of the citric acid cycle is taken away for biosynthesis, it must be replenished again in catabolism. And we usually call that property anapleretic property of the citric acid cycle, whereby a particular reaction, a system ensures the adequate supply of an important metabolite at any point in time. That metabolite cannot be lacking. A very good example is that if oxaloacetate is removed by carboxylation, oxaloacetate can be removed for the synthesis of an amino acid. It has to be replaced by carboxylation of pyruvate. So there is always the constant supply of this metabolite in and out to maintain the cycle. So if we look at this now, this picture shows us the central role of tricarboxylic acid cycle or citric acid cycle in catabolism. Let's start from this side. Now, this is carbohydrate. Of course, carbohydrate is broken down to glucose. Glucose is broken down in glycolysis to phosphoenol pyruvate. Phosphoenol pyruvate is broken to pyruvate. Pyruvate can now get into, like I told you, pyruvate is permeable. We'll get it through the walls of the mitochondria. This is the mitochondria. Remember, this is the mitochondria now. This is the mitochondrion. And here it can be converted as CYcle-2, just like we saw, and it goes inside the citric acid cycle. Now, what else can join? Look at what happened here. Many amino acids can join pyruvate. Particularly, we call these ones the glucogenic amino acid. Alanine can get into that place. Threonine can get to that place. And this will happen through transamination. Threonine can get in. Serine, cysteine, and glycine can get in. And all of them can join in again. What about the lipid? Lipid, of course, are broken down to fatty acid and glycerol. Fatty acid can easily get into this, and the beta oxidation happens inside here, and then what happens? Again, converted to acetyl-CoA. Okay, all amino acids too can go directly. We call these ones ketogenic. Those ones that connect to the citric acid directly. Asparagine can go to aspartate, aspartate can go to oxaloacetate, oxaloacetate can go to malate. Malate can easily get into the citric acid cycle. It's a part of citric acid cycle. Again, look at these ones. Tyrosine and phenylalanine can be converted to fumarate. And fumarate is also part of citric acid cycle. What about threonine? Threonine, valine, isoleucine, and methionine, all these amino acids can be converted to succinate-CoA, and all of them can also go back into the TCA cycle because these ones are also what we call the ketogenic amino acid. Ketogenic amino acids are those amino acids that can join the tricarboxylic acid cycle, whereas the glycogenic are those ones that join the glycolytic pathway. Now, what about this one? Let's see other things happening too. Now, what about isoleucine? And leucine can also be converted to acetyl-CoA, and acetyl-CoA is a part of citric acid cycle. Tyrosine, lysine, phenylalanine, and tryptophan can also be broken down to acetyl-CoA. Acetyl-CoA is permeable to these walls and can also get it. So, every catabolic pathway has a link that must be connected. All the three fuel molecules from carbohydrates, fatty acid, or lipid, and proteins. Vis-a-vis amino acids are all connected into this, making it an important central metabolic pathway for catabolism. Again, let's look at what happens in anabolism. Of course, like I said earlier, before I look at the anabolic part, remember I told you that it maintains a constant supply of this metabolite. If one is removed for anabolism, it has to be replaced by catabolism. Look at what's happening here. Now, this is the citric acid cycle. Now, at times, this citric acid cycle can be replenished. Now, the mammals, look at the mammals. Mammals cannot convert acetyl-CoA. Mammals cannot convert acetyl-CoA to oxaloacetate. And mammals, like the human beings particularly, cannot convert acetyl-CoA to do what? To this. However, they can do one thing. What can they do? What they can do is that they can convert pyruvate. Pyruvate can be carboxylated with carbon dioxide. Hydrolysis of ATP is used to be converted to oxaloacetate. And in making sure that there is always the constant supply of this. Always a constant supply of this. So that is what makes this a very wonderful pathway. And alpha-ketoglutarate can be transaminated to glutamate. Glutamate is usually the first amino acid that is synthesized during the synthesis of amino acid. And we're going to talk about this by the time we get there. All right, so what is the role of glycolytic part of, what is the role of citric acid cycle in gluconeogenesis? We talked about this in gluconeogenesis again, but it's good I told you. Remember, I told you in gluconeogenesis, the first two reactions of gluconeogenesis are taking place in the mitochondria. And what is the reason? Because those enzymes that needed for that reaction to take place are located in the mitochondria. Therefore, those reactions are taking place there. And then, if you get to a point, it leaves it. So let's see what is happening there. Remember, in gluconeogenesis, you are synthesizing carbohydrate, particularly glucose, from non-carbohydrate sources. And then pyruvate is usually seen as the first product. What is happening here? Let's see what is happening here now. Malate easily can leave the mitochondria and then be converted to oxaloacetate. If you get to oxaloacetate can be converted to phosphoenol pyruvate by the phosphoenol pyruvate carboxylase. And then this cannot go back to, by gluconeogenesis, can form glucose, which is a carbohydrate. There's another source too. Another source too is that, what happens here is that, look at what is happening here, is that pyruvate can be carboxylated. This is the one you should also see earlier. This is happening inside the mitochondria now. Can be carboxylated to oxaloacetate. Oxaloacetate now can also do what again? Can again be converted to phosphoenol pyruvate by the enzyme carboxykinase. And this again uses ATP. And PEP is permeable to mitochondrial wall. It's going to get out, join the gluconeogenetic pathway again. So this is the link of citric acid cycle to gluconeogenesis. Excuse me. Now, what is its link to general anabolism? Excuse me. Now, the link to general anabolism is also not, it won't also be overemphasized. Look at what is happening here. It represents a common source of so many intermediates for the biosynthesis or anabolism of fuel molecules. The carbohydrates, the lipids, and the proteins again. Let's look at what's happening. This is TCA again, taking place in the mitochondria. Look at what happens here. Now, again, remember, for lipid anabolism starts from, most anabolic pathway takes place in the cytosol, right? But it starts from what? The mitochondria, and then moves to the cytosol. So look at what is happening here. So at this point again, so this is carboxylic acid cycle. Now, look at what happens here. Citrate, which is a part of CTA, leaves the mitochondrial walls, gets outside. Citrate itself is now converted to oxaloacetate. In that process, it is broken down to acetyl-CoA. Two acetyl-CoA molecules can join in a complex process of fatty acid anabolism to form fatty acid. And this oxaloacetate can now be converted to malate. And this malate can also come out from this, and malate again can also be taken to form the pyruvate. So this is just very linked. The importance of mitochondria cannot be overstated in general metabolism in biochemistry. So what is the generalized central role in anabolism? But we just looked at only the fatty acid, the lipid. Let's look at the generalized. Remember, we said it is a starting material. It provides starting material for all biosynthesis. Now, let's look at how that is happening for biosynthesis. That biosynthesis didn't come out right. Biosynthesis. Okay, let's see what's happening. So let me start from one side. Let me start from here. Now, this is oxaloacetate. Oxaloacetate can be converted to PEP. Remember, this is gluconeogenesis. It's going to leave, and then here gluconeogenesis is going to produce this. It can also go through this way. PEP can also go through this way to form various amino acids like phenylalanine, tryptophan, and tyrosine. Again, look at what's happening. Oxaloacetate can be converted through transamination to aspartate. Aspartate can then be converted to aspartate. Aspartate can now leave and now be converted back to oxaloacetate. Then this oxaloacetate can also be transaminated again to aspartate. This can also be done by malate, which is also a part of this, can also leave and then be converted to oxaloacetate. And if you have aspartate again, aspartate can result to the formation of other nitrogen-containing molecules like the pyridines, lysine, threonine, methionine, isoleucine, and asparagine. Okay, that is one part. Let's look at what is happening here. Now, of course, we have, remember, pyruvate can form acetyl-CoA. Pyruvate itself can leave. Pyruvate here can also be used to form different amino acids like lysine, valine, and isoleucine. It can also usually forms directly alanine. The transamination of pyruvate forms alanine directly. And then alanine can also get through some other series of reactions to also form glycine, serine, and cysteine, which are all part of amino acids, which will also act to build up the proteins. Now, what about this side? Now, citrate can leave the mitochondrial cell. Citrate cannot be converted as acetyl-CoA, and acetyl-CoA can now go through series of reactions to form both the leucine and lysine, which are amino acids. It can also go series of reactions in lipogenesis or synthesis of lipids to form fatty acid and the steroid as well. And then let's know what's happening here. Isocitrate too can leave the mitochondrial wall, converted to alpha-ketoglutarate. Alpha-ketoglutarate can be transaminated to what? Glutamate. And glutamate can now be converted to other amino acids like proline, arginine, and glutamine. And then not just that, as transamination can also occur by inside the mitochondria of, if you transaminate alpha-ketoglutarate, it forms glutamate. This glutamate can leave to join this as well. Then again, succinyl-CoA can also be converted to alanine, and if alanine can leave and also help in formation of porphyrin. Porphyrin is the prosthetic form part of the heme group in molecules like the myoglobin, and we talked about this already, the myoglobin and the hemoglobin that help in the transport and storage of oxygen respectively. And then, of course, this is your, again, remember this is your mitochondria. Again, this is the inner mitochondrial membrane, this is the outer mitochondrial membrane. This is those infoldings that help you to develop a high surface area for all these reactions to take place. And finally, what is the link of citric acid to oxygen? We talked about this in the beginning of this, so I want to end with it again, the summary. Citric acid cycle is considered to be part of aerobic metabolism. Of course, it is part of aerobic because it involves the reduction of oxygen. It is this process that links the electron. It is the process. Okay, citric acid cycle is considered to be part of aerobic metabolic process because of its link to the electron transport chain and oxidative phosphorylation. Now, citric acid cycle provides that vital link between the chemical energy of the nutrient, of course, the chemical energy of nutrients, and the chemical energy of the ATP. Because what the body wants in this metabolism, catabolism, is to generate this ATP. And this ATP is used to power metabolic activity and also used in synthesis of molecules. Of course, NADH and FADH, the nicotinamide dinucleotide reduced and the flavin dinucleotide reduced, are two important cofactors that are generated in the citric acid cycle. And it is only these two guys that are generated here that will help to pass electron to oxygen in the third part, in the last part of, or the third stage of metabolism that we're going to be talking about in module 20 or chapter 20. Look at what happened. After citric acid takes place, these electrons are now being carried by these two guys, plus some of the ones that are released by fuel molecules a little bit. Most of them are generated. All these electrons are now being carried in the electron transport chain, and the movement of this electron creates that pH gradient. That pH gradient provides the energy that is needed for the coupling of phosphate and ADP to form ATP, which is the ultimate goal of metabolism. And having said that, once again, thank you for listening, and we'll come to the end of this chapter, and do have a wonderful day ahead of you, and bye at this point.